Okay, good morning everybody. As each week, do you have questions? So anything you want to discuss, you want to ask when going through the slides over the week? Any exercises you did do and you want to present or discuss or ask questions about? Please?
I have a question for exercise 5-6.
Okay.
It's about requesting an overlay, and I wasn't quite sure what that was and tried to find it in the slides or in the slides and couldn't find anything about that. Maybe I missed something?
Requesting and overlaying. This is the message service. So it's about, let's see. This procedure. So the name comes from we request something, we get an answer, and the user does overlay in the sense of adding up bit by bit more to the answer he or she gets. Then maybe we just start here and just go very quickly through what we did last week. Last week it was about recipient anonymity, protection of the recipient. Mainly we had two procedures to do it. One was to broadcast. And broadcast then means everybody gets the same information nearly at the same time. Nearly at the same time means it's so much or so close at the same time that the moment of an answer mainly doesn't depend on the subtle time differences. Otherwise, broadcast wouldn't help you a lot. Even if it's broadcast in the long run, if different stations get the messages at essentially different times, then they will answer to the messages at essentially different times, so identifying the sender or the recipient in the round before, right? So broadcast does not only mean everybody gets it in the long run, but that stations get it nearly at the same time, or if you can provide for it exactly at the same time. Second remark, of course, a modifying attacker might try to cause broadcast not to happen. He may try to cause that some stations get it, but not all of them. Or that some stations get it earlier and some stations get it later. And again, the reaction of stations would depend on whether they get the message, or it would depend on when they get the message. And again, this could identify the recipient. So, broadcast here is security critical. The consistency of broadcast is security critical. About efficiency, depending on the network, broadcast may be efficient or not. And certainly, depending on the connectivity, whether all stations are online all the time, broadcast may be a good idea or may be a bad idea. If, for example, 20% of all stations of the network is offline, then doing a broadcast to the 80% being online probably is not really useful. First, because recipients are not really well protected. Secondly, because the other 20% sooner or later want to get the message. So what do they do? Are you going to repeat the broadcast? How to handle this? So broadcast may be a good idea if it's supported by the network or if all stations are online all the time. Then we had a second solution to mainly the same problem. And various broadcast is a kind of push technology. You broadcast to every station which might be interested in the message. Here in the message service, it's more a kind of pull. Stations ask for messages in a way that the message service doesn't learn for which messages they are asking. Pull, of course, has the advantage that it's the user station which decides when to ask, when to pull. So if we assume that servers are up and running all the time, then of course the world gets much easier that way. If the user station is interested in some message, and if the user station is up and running, then it's going to query the message service. So pull has less demands on the availability of user stations, because the user station can decide when to request the service. Then we did some improvements, some efficiency improvements. We discussed implicit addressing, which, as I said, is not really well worked out. It's an area of current study, so maybe if you want to do something there, you're very welcome to do so. Then we discussed a little bit about fault tolerance. Why? First, because errors might undermine security. So if we are talking about security, somehow we have to consider errors. And secondly, because usually techniques for anonymity make provisioning of service more difficult. To give you an example, or two examples. In broadcast is only a success if it's broadcast to all stations. Usually, if you don't care about recipient anonymity, broadcast is successful if you broadcast to all stations which are interested. Usually in a broadcast there's no real need to send your message to a station which is just not interested in the message and throws it away. If you are talking about recipient anonymity, it's essential that each station gets it. Therefore, errors, which maybe you can ignore if in normal broadcast some stations miss a message, rarely, not too often, then maybe you can ignore it. If it's about security, probably you better don't ignore it. Second example, Usually, if you are querying a server for a message, what has to function correctly in order that you get the message? Your station has to be okay. The network has to function. And the server has to function. And then, hopefully, you get the message from the server. It's transmitted over the network. It reaches your user station, and you receive it. Fine. If you consider the message service we had here, what has to function? Not only one server, but all servers you are querying. And all these servers have to do the right thing, not to do any error. Because if only one of them does some error, if you finally add up all the answers you get, the sum will be random, or will be the wrong message. So again, we see that recipient anonymity requires that more stations, in this case more servers, function properly. And it's pretty clear, the more stations have to function properly, the more demanding this requirement is. Therefore, if it's only one server, your network connectivity, and your user station, then maybe given today's technology, there's not a need to make too much fuss about availability, because usually servers are running, usually networks are functioning, and hopefully your user station functions as well. But if you are talking about anonymity and one entity, one station is replaced by many ones, in this case one message server where you could query a message is replaced by several servers or even many servers, then talking about fault tolerance is a necessity. So we did talk about fault tolerance. Okay, so this we achieved last week. And then we started talking about protecting the sender. We talked about dummy traffic, and that this is conceptually very simple. Stations are just sending messages which are mainly meaningless. Hopefully they are not meaningless for an observer, but they don't reach or they don't inform any station within the network. They are just ignored. Sometimes I have the feeling that Twitter is a very large experiment in dummy messages. But of course, those people using it appreciate what they get. Or, okay, I shouldn't comment too much about it. So the next question is, if dummy traffic is an awful waste of resources, can we use what one station sends as a kind of dummy traffic for other stations? So can stations sending protect the anonymity of each other, in the sense that a message could well be sent by any one of the sending stations? If this works, of course, it's a lot more efficient than having dummy traffic. First, it's only transmitted what is useful. Secondly, if a recipient receives a message, and he cannot figure out who did send it, then this provides sender anonymity in a strong sense. If it's only dummy traffic, then in principle the recipient could figure out who did send the message. It's just the sender's address who tells that. And then if it's meaningful, then okay, this meaningful message comes from that sender. The oldest concept of trying to use what one station sends as a kind of dummy traffic for another station is the so-called ring network, which was in fashion when I started, so I did it quite early in my academic career. The idea at that time was that stations should be connected by media in a ring fashion. So all messages should run around the ring, usually either by the sender or by the recipient. They are taken off the ring after they made it, and then the next message may be sent. So what is the idea? It's pretty clear. If you have an attacker before a station and after a station, there's no much sender anonymity, or we could even be more precise and say there's no sender anonymity at all. Because if I would see this goes in, if I can check, oh, this goes out, then I can just compare. And the difference is what this station 1 is sending. So the best we could hope for is if you take two stations, I call them station 1 and 2, and here is monitored what goes in, here is monitored what comes out, and the best case we can achieve is that these two attackers working together, these two attacking stations working together as the attacker, can't figure out whether a message which has been sent in here is sent by station 1 or station 2. And hopefully if you can prove that, this would generalize. If an attacker is before and after 3 stations, then hopefully he couldn't figure out which of the 3 stations did send it. And if it's 4 stations, then and so on and so forth. So let's consider the most difficult case for the designer of the security mechanism. Let's consider the case that an attacker is before and after 2 stations. How can he try to identify who did send a message which comes out here but didn't come in here yet? So one possibility to identify is at the signal level. It might be that bits which come here have a different shape whether they originate within station 2 or whether they originate in station 1. Could be that bits have a different shape. For example, if they are generated here, maybe it's a longer distance, maybe the amplitude is slightly slower, maybe its shape is more, let's say, less precise, whatever. Whenever this attacker can make out a difference, depending on whether station 2 did send the bit or whether station 1 did send the bit, then the game would be over. Because then at the signal level, the attacker could decide which station was the sender. So the first requirement we need is digital signal regeneration. which means that the analog characteristics of bits are independent of their true sender. How to achieve that? A way would be that what station 1 sends is stored here in station 2. Now it's in storage as any message which originates in station 2 finally will be in the storage of station 2 before being transmitted. And then it's undergoing the exactly same process of being sent. This should give the result that all the bits sent by station 2 have the same shape, because they all originate from the storage of station 2. So conceptually, digital signal regeneration is simple. In practice, is it done? Depends. What is the requirement in a ring network usually? Or what is a requirement in a network usually? We want to have short delay, right? Good throughput, short delay. Usually what is more important? Short delay. Because usually if throughput is not as good as you would like it to be, then maybe you put several networks in parallel. That way you get more throughput. But if the delay is not good enough, putting more networks in parallel usually won't help you. Okay, so delay is critical. So what would we like to be? What would we like to happen? We would like that if station 1 is sending a bit, maybe we are storing 1 bit. But surely we shouldn't store the whole message station 1 is sending in station 2 before we start to relay this message towards the next station. So what I told you, that conceptually each message is stored, each message sent from station 1 is stored within station 2. Conceptually easy, but probably won't give the delay you would like to have. It's causing too much delay. And now it gets tricky. Because different kind of ring networks do timing differently. How could you do timing? The simplest way, and this is what the token ring does, the token ring was the fashionable network at that time. The token ring does, hey, we get bits, station 2 gets bits from upstream, and these bits take with them a clock rate. They get with them timing information, which surely is a kind of necessity, because how do you detect different digital values if you haven't a clue about timing? And the easiest way is, if you have a clock here and a clock there, that clocks are not perfect, so you need some kind of adaptation, that this station is adapting to the clock here. One way to do is make this signal, which is transmitted from station 1 to station 2, carrying time information, making the station 2 adapt to it. This is indeed done with the token ring. And this kind of adaptation to the time here usually is not perfect, because the time information to some degree depends on the bit values transmitted. For example, if you say timing information is when are we crossing 0, now depending on what kind of low and high you transmit, this crossing 0 may be slightly shifted by the values you are transmitting. So in the token ring, the problem is that station 2 wants to adapt to the clock rate of station 1, and this depends slightly on the bits transmitted here. And now of course we have a problem, because if timing here depends on the bit values transmitted here, then an attacker might see slight differences in timing, which tell the attacker what have been the bit values here, which is helpful to trace which station was original sender. So token ring is not a good implementation of digital signal rate generation. There are other implementations of ring networks, for example, FDDI does it different. In FDDI you have timers, clocks, and to adapt to small differences here, to clock skew, you have a kind of elastic buffer. So you are not changing the clock here depending on what you receive. The clock here is just running as it runs. But you're using a small elastic buffer of a few bits to adapt to clock skew. And this would be a perfect implementation for digital signal rate generation, because the clock here is just running. It's not depending on what is transmitted here. So this was the explanation of digital signal rate generation, and using two examples, I told you digital signal rate generation may be provided for in practice, and there are situations where it's not provided for in practice. So this is the bit level. Of course, if you cannot provide sender anonymity at the bit level, in some sense the game is over, because what can you do on higher levels? Later we will see that there are possibilities you could do at higher levels, but at the moment probably nobody of you has any clue what to do if I can trace the bits to the sender. Let's assume at the moment we can't trace bits to the sender, so digital signal rate generation is in place. What else could happen? Usually in a ring network we need something like a medium access protocol. We have a kind of protocol which tells us which station may send when. In the token ring, for example, a token is passed from here to there, to there, to there, and again. And the station having the token may send. Of course, the question is how much? If you get the token, you may send. Does this mean you are entitled to send one message? Does it mean you are entitled to send a millisecond? Does it mean you are entitled to send forever, as long as you think you have something to say? If you think practically and think about professors, it's very dangerous telling an entity it may talk as long as he or she wishes. Because, it's only in the end one entity talking, and sooner or later nobody is listening. So it's not really a usable system if we say stations may send endlessly, because they may just block others from sending. And if you look at the human level, it may just frustrate other human beings. Let's assume token passing means if you get the token, you are enabled, you are allowed to send one message. This would be probably the simplest protocol. Let's assume we have a situation in which we have something to send. And let's assume the attacker knows how many stations we have in the ring. What will happen? The token is passed from here to there. This station will send. The token is passed further to that station. Station 2 will send. The token is passed further, this station will send. And so on and so forth, until finally each station which is in the ring did send. And now, if you know, the rule is after you got the token, one message at most. If you know how many stations take part in the ring network, if you pass the token and before you get it back, the same numbers of messages passes by, as there are stations in the ring, you know everybody did send just one message. And even more, you know the first message you're going to hear is a message from the station downstream. The second message is the message from the station after it. So if everybody sends a message, there's no sender anonymity. And digital signature regeneration doesn't help, because now it's just a problem of the medium access protocol. So what to do? You could do, okay, let's allow that each station sends 2 messages at most. But now again, I could argue the same way. If each station sends 2 messages, same argument. And it doesn't change if we are allowing 3 messages, 4 messages, whatever. So whenever I have a fixed number of messages which are allowed to send, and whenever I would have a situation where all stations want to send as much as they are allowed to, then it breaks down. Okay. Now let's assume the number of messages is somehow unlimited, which a station may send. So now the rule is, if I get the token, I'm entitled to send all messages which I just stored for transmission. And then I'm going to pass the token further. How does it look like? So here I store messages in the way that I assume I have a kind of container. Containers may be empty, or they may be filled with a message. So the containers flow around the ring and by stations may be filled and emptied. Time goes down here. So this container is here, that or that container is there. So here I have different possibilities. This container may be here, and then it circles, and maybe it reappears the container here. Then we have these possibilities, that, so. So this is all possibilities which might happen if an empty container goes in, until finally an empty container comes out. And now I assume in between there are n messages sent. And there are different ways how that might be done. One way is that we say, hey, in the first round, here we have an empty frame, which then means that station 2 is going to send all the n messages, because station 1 didn't send something. So the right to send is passed from station 1 to 2 without station 1 sending anything. So one possibility is here we have the empty string, and then here we have M1, so it's going to circle, and then it comes in here, and then it's pretty clear. Here we have M1, so M1 is transmitted until the station which originally did send it, and then it's replaced maybe by another message. In this case, it will be replaced by M2, makes it around the ring, comes in here, will be replaced by M3, until finally station 2 has sent all the messages and outputs the empty frame. This was one possibility. Another possibility is that in the first round, here we have message 1. That is, the first station is sending a message. Then, of course, this message, M1, is just relayed by station 2, goes around the ring, and can now be either get the empty frame, in this case station 1 has nothing more to send, it's just outputting the empty frame, or station 1 has more to send, message 2, so sends message 2, and again it makes it around the ring. That is, if station 1 is sending, sooner or later it has to pass the empty frame to station 2. If it's happening somewhere in between, then the rest of the messages is to be sent by station 2. If passing it to station 2 only happens after station 1 did send all the messages, then station 2 will just relay the empty string, because in this case all the messages are sent by station 1. So if it's about n messages, mainly we have n plus 1 alternatives. What might have been the situation with respect to sending messages? So because we have the first possibility and we have the last possibility, we can argue that each message can be sent by each station. But this is surely not what we really want. We would like to have more. What we would like to have is each message can be equally well be sent by each station. And with this kind of protocol, we can't achieve. Why? If we have a long sequence of messages, then I would argue the early messages are much more likely to be sent by station 1, whereas the later messages are much more likely to be sent by station 2. And in any case, we have arguments that we know that if, for example, we know by what kind of procedure ever that message 2 is sent by station 1, then we know message 1 is also sent by station 1. That is, this passing of the token along the direction of the ring gives us a dependence of which station can have sent which message. So this kind of procedure is okay, so we can always argue. It could be that everything is sent by station 1, it could be that everything is sent by station 2, but it's surely not perfect in the sense each message can be sent equally likely by station 1 or 2. And in particular, we have a kind of dependence between different messages. So for some messages, if we know who did send it, we know the sender of other messages, which may be quite risky if you think that you're using that kind of communication network for non-anonymous communication as well. So for some messages, you know the sender. Now the protocol gives you some inference about other messages. Just as a side remark, if you make more complicated ring access protocols, for example, that after, or here we optimize that each message goes only one time around the ring. If you are prepared to do twice as much expense that each message may go twice around the ring, then you can overcome that kind of problem. But now it gets involved. If you want to learn more about that, then read my PhD thesis. So why I didn't explain it so deeply? Not because I think that ring networks are mainstream today. They are not. But in this first approach of providing sender anonymity, you can learn a lot of problems, a lot of subtle problems. So digital signal regeneration is something you should be aware of. If I can identify senders at the signal level, the game is over. Does this have something to tell us today? I would argue yes. If you think about radio networks, usually, even if you are using devices produced in really large quantities, each different device has a different radio signature. That is, the shape of signals will be slightly different, even if you have the same type of device produced on the same day. Of course, Now it gets us into a discussion about quantities. How different are the signals? How much does it cost to evaluate the difference? But in principle, it could be done. Secret services tell us that they can track individually cell phones within hundreds of absolutely equal cell phones, or seemingly equal cell phones at the signal level. So what we usually do in computer science, that is, we abstract away, if it's about bits, we are abstracting away the particular shape of signals. This, in some sense, is a really good idea, because digital storage is about abstracting away all the shape of signals. Great. Gives denser storage, makes digital technology cheaper and more powerful. Great. But if it comes to some security properties, this may be very risky. Because if all the good guys agree we are going to abstract it away, it's really hard to make sure that the bad guys abstract it away as well. Maybe really risky. So I think the story about digital signal regeneration is really a story which has a fundamental meaning to security and computer science. Abstraction is great, and I think whenever we achieve something in computer science, typically it has to do with abstraction. We can't do without. But if it comes to security, we have to be careful. Okay, so this was one lesson to learn. Second lesson to learn is, even if you have at the bit level anonymity, it may well be that higher protocols, that protocols at a higher layer, undermine anonymity. I think the most prominent example was the token ring, where you are entitled to send just one message after you get the token. Then if every station just sends, because it has something to send, if the number of stations is known, which is obviously something an attacker would probably know, then there's no sender anonymity in spite of digital signature generation. So anonymity seems to be a property, and indeed it is, where it's not enough that you provide for it at one layer. Probably if you want to keep it at the application layer, you have to keep it at all layers in between. So anonymity is a property which touches all layers. At least all layers above the layer which provides anonymity. Again, this is something in computer science we don't like. How do we build layered systems? We say, hey, a layer has to implement some properties which then on we can take for granted in the higher layers. For example, reliable transmission, so some layer does error correcting coding, maybe it does a retransmission, whatever, then the higher layers may assume that transmissions errors don't exist. Nice. Very nice, because from then on you can design your protocols as if transmission errors never would occur. Great. So this gives us a possibility to deal with one issue in a particular layer, solving one problem at a time. Right? Sounds great. If you're talking about anonymity, this is different. You can't build a layer which provides anonymity and then, from then on, take anonymity as granted. Doesn't work. I'm going to an extreme case. If at the application layer, by social engineering, you ask someone, hey, by the way, what's your address and what's your birthday? And if the person just types in the address and birthday, then probably the game is over. And depending on how clever you ask, it's easy to achieve. So, and I could also, as I mentioned here with the protocols, I could also frame it in a technical sense and not in a human sense. Same problem. So, with respect to security, and in particular to confidentiality properties or anonymity properties, what we usually have in computer science, that you try to solve a problem within a particular layer, and then you are able to forget about it. This does not work. It's a pity. I would be very happy if it would be different. It would make engineering much easier. It would make engineering much more enjoyable. But sorry, it isn't. And now there are two possibilities how you might behave. One possibility is just to say, oh, this is not really a nice problem. I'm going to ignore it. And this usually is what the approach people take. If they don't like it, they are just going to ignore it. Of course, then the game with anonymity is over. If you decide to ignore it, then you decided anonymity will not happen. So I don't see a better approach than to rethink anonymity at each layer and at each application. And what makes it even worse, even the interrelationship between different applications may have consequences for anonymity. So if in one service, maybe Skype, you tell, hey, this is my birthday and this is my nickname, and in another service you tell, hey, this is my nickname and this is my address, then an attacker who takes part in both services may use your nickname to link, and then he has your birthday and your address. And quite probably, then the game is over, with respect to anonymity. Okay, so summarizing, I did give you an intro in the ring network, not because I think it's of much practical relevance today, but because usually if you look at old concepts, these old concepts gives you the most obvious solution and the limits of this kind of solution. And here I'm interested in spelling out the limits. Okay? I should mention that, of course, what I framed in the example as a ring network, which was in fashion, let's say, in 1983 when I started with the whole game, Today, we have another technology which might be used to physically provide sender anonymity. Today, it's the cable networks for TV, which historically were only used in one direction. From the head end, the TV distribution network, towards the user. In the meantime, they are upgraded for two-way communication, which basically means it's a tree-shaped network that whenever two branches on the upstream are connected, you have to decide what to do. So if you would do that kind of protocol in a clever way, it could provide, if you're only allowed to tap at higher levels, some kind of sender anonymity for all those being in the same part of the tree in the lower level. So again, I think something you learn structurally can be applied in more modern technology again. And even in some research papers, if you Google for the name Crowds, which was a system published for anonymous browsing, you will rediscover some of these very old ideas. Now about fault tolerance. And maybe this ring network is again a very, very obvious example why fault tolerance is essential. Let's go back. If you want to have a lot of sender anonymity, what would you need? A very, very large ring, right? The more stations we have in the ring, the more sender anonymity we might be able to achieve. And now it's pretty clear if you're just building ever larger rings, then what will happen? Okay, first delay will be increased, so probably this isn't really a good idea. But secondly, if you would build ring networks of, let's say, 100,000 stations, then it never ever would function, because some station would be misbehaving at least at every time. So again, fault tolerance is an issue. So what to do? In the ideal case, for each possible error, nevertheless you would provide anonymity, and hopefully in spite of the errors, we could provide some service. And now we have a dilemma, we have a problem. Usually for anonymity, we would like to have little global information, because if we would have global information, we would know who was sending. If you would have a global view on your network, you would know what's happening. For fault tolerance, it's the converse. Fault tolerance gets easier if you have as much global information as possible, because then you know which stations or which parts of stations are faulty, how to repair them, or how to do some routing around these faulty parts. And what we have here, and what we will have in similar form in other techniques, there are two ways to tackle the problem, two principles. One possibility is to have a kind of fault tolerance through weaker anonymity in a single operational mode. So we have to trade some anonymity against better availability. So you give away some anonymity for getting better availability. Or you say, hey, we have at least 2 operating modes. So one operating mode for fault diagnosis and fault tolerance. So if it's a separate mode, if everybody knows this is a separate mode, nobody will in this mode of operation send sensitive information. So privacy is a non-issue in that mode. So you can do arbitrary detailed analysis in this mode. And hopefully after you're recovered from your errors, you can use your anonymity technique again. But if you have these 2 modes, I should mention it's now only against errors. It's surely not against attackers. In particular, it's not against inside attackers, because an insider has to know in which mode we are operating the system. He has to know whether it's in fault diagnosis mode or in usual sending mode. And of course, a clever attacker who wants to bring down the network will only induce faults, will only misbehave as a modifying attacker if it's in anonymity mode and not if it's in fault diagnosis or fault tolerance mode. Okay, so far the principles. Now a particular technique. So if you want to build a ring in a way that lines and stations may fail, one way to do it is just you have your ring. I will call it the outer ring in the sequel. And you have a kind of inner ring, that is, you're not only connecting a station with the next station, but you're also connecting it with the station behind. And then if you do that, and if you have an uneven number of stations, surprise, surprise, the inner ring will close as well. So if you start here, you go the inner ring, oh, here we start. So that, okay, now we are back. So if you are using the inner ring, you have to make it twice around the ring. So maybe delay in the inner ring will be slightly higher. Same number of stations. So if delay mainly is induced by stations, then it would be mainly the same delay. If delay is induced by the length of the cables, then the inner ring has twice as much delay. So this is a usual, this has been a usual technology in ring networks to make them fault tolerant. And now we can discuss what to do. Let's assume a station fails. What would we do? You would just use the link which skips this station to close the ring. And that way, if a station fails, we could maintain a ring of all other stations. Surely transmission bandwidth would be halved. We have now only one ring instead of 2, but still we have a ring. Let's look here. Let's assume a line breaks or gets inoperational. What to do? If it's a line in the outer ring, the conceptually easiest way is to say, okay, ignore the outer ring, just use the inner ring. And as I mentioned, it's closed, so we have a ring. And now, of course, if both happens, at least in general, if one link fails and one stations, still in many situations we could reconfigure. And just to give you an idea about the basic problem we would like to have, let's assume we have this link not functioning, but still we want to reconfigure the outer ring. The inner ring is easy, you have not to do anything. But let's assume this link in the outer ring fails, and still we want to keep usable the outer ring, which gives us more flexibility in how to react on faults and errors. One way to do it is to say, hey, the station before sends half of the traffic to this station, and this station here sends the other half to that station. This station here is reassembling the halves and sends it back in a normal fashion. Here it's distributed here and there, and here and there, as mentioned, it's taken only half of the traffic. What do we achieve that way? First, each station gets all the traffic. So with respect to recipient anonymity, to the broadcast property, we have within the ring network no change. All stations get all traffic. With respect to sender anonymity, seems to be okay. If here some bits arrive, it could be that they come from this station, but it could also be that they come from that station and are just relayed. The only thing this station knows, if a bit arrives here, then it's not coming from station S1, I assume. Oh, is this true? Assuming everything goes one time around the ring, if it comes here, then it's not from that station. So in this scenario, sender anonymity is decreased slightly. So if here we have a failure, the sender anonymity of this and that station, the sender anonymity of the two stations sharing the link is slightly decreased. Okay, this as one possible kind of approach what to do, and some analysis what is the price to be paid. Now let's go a little bit backward and discuss modifying attacks. Or maybe we go back even a little bit more here. If we talk about a ring network, you have some kind of standard how to build it, and then probably, if you consider a station, it has to be clear whatever the inputs are to the station, it has to be specified how the station shall behave. And in practice, often not all possible inputs are specified, but sometimes people only say, hey, you only have to spell out what inputs really appear and specify what the station does on that input. And now your engineering gets somehow risky, because you only consider inputs which you expect. But if errors occur, or if attacks occur, maybe your station gets a combination of inputs you did not expect. And nevertheless, it should be clear how to behave. So, if you discuss modifying attacks, in some sense, for sender anonymity, we have at least to extend the access method. Because if an attacker, a modifying attacker, does not adhere to the access protocol, somehow we have to decide what to do. And if we want to achieve some kind of sender anonymity against the modifying attack, the modified access protocol has to have the anonymity property. Recipient anonymity, hopefully if each message makes it one time around the ring, recipient anonymity should be provided for. And what is nice here with the ring network, that these two things, the recipient anonymity and the sender anonymity, in some sense are tied together. Going back. If the attacker passes a message here, it's pretty clear that this message from here will be transmitted to there. That is, the same number of stations, the same set of stations, which is hopefully providing sender anonymity to each other, also provides recipient anonymity to each other. So the rule that this station transmits to that station both gives sender anonymity, if you have digital signal regeneration, if you have the right kind of access protocol, and it gives recipient anonymity. It just makes sure that if this station is going to get it, that station is going to get it as well. Okay, so in the ring network, it's obvious that sender anonymity and recipient anonymity are provided for under the same attacker model, which is nice. Service delivery. What do you do if you are operating a ring network and if it doesn't work? Let's go back. You send in a message here and it does never come out here. Then what would you have to do? Find out whether it has been transmitted here. Because only then you can say which of the two stations did misbehave. That is anonymity, which is a positive property, maybe for some usage of the network, may be a very bad property for accountability if something goes wrong. So, if these two stations both argue we are fully okay, if, after some measurements, you would say the link between the two stations is fully okay, but nevertheless it doesn't work, then probably what you know is at least one of the two stations is a modifying attacker. So what to do? Hard to do any usual stuff here, because usually the ring network, as I described it here, is quite static. It's the cabling which is done in a ring shape. So it's hard to change anything. The topology is at a very basic level. It's very hard to change. Maybe just to give you an idea about office buildings. The token ring network by IBM was designed for office buildings, not private flats. And if we are now talking about sender anonymity, probably what you have in mind is private flats, private users looking for their privacy. IBM designed the token ring network for office buildings. And how did they do it? Maybe we do some drawing. In an office building, you had usually some central point where all the cables end up in one room. Usually private branch exchange, here you had a kind of telephone center, telephone switch often. And then maybe we had many different stations within the office building. And what you had usually is a pair of copper wires. And often you had more than two wires, because cables usually had 4 or 8 wires. And what IBM thought was, hey, if we take some spare wires we have anyway, we connect them such that and now we have a large ring, right? If you do it in a clever way. But from an attacker model, of course, this is not really a ring, because if I get access to this central room, I can tap the ring before and after each station, right? Because it's just going through this central room. So this is a kind of ring network which, if you're looking for realistic attacker models, I would argue this is not really a ring network. This mainly is a kind of star-shaped network, star-shaped ring network. So from a privacy point of view, from an anonymity point of view, it's a nightmare if you do it that way. From availability, from reliability, from fault tolerance point of view, hey, this is really nice. If this station either breaks down, is powered off, or whatever it is, what do? You have a switch here, you just shortcut. And this station now is offline. So if you do it that way, it's very, very easy to reconfigure the ring. And what is a dual property? Of course, it's very easy to tap before and after each station in this ring. So you see, in such a ring, I could be really easily reconfigure who shares a line with whom. But that kind of ring wouldn't have, let's say, a realistic attacker model which makes it difficult to tap before and after a station. So, after that kind of discussion, hopefully we learned mainly a lot of problems. And it's my feeling that with this very basic technology, because the ring network is so apparent, it's so close to physical reality, these kinds of problems are easy to understand. And what we will now do is come to a much more powerful, and I would argue much more clever technique invented by David Chaum 2 years later. It's now 1985 in contrast to 1983. And David Chaum will come many times to this name. He did a lot of good discoveries in this area. Invented a concept which I called superposed sending. David Chaum called it the DC network, the Dining Cryptographers Network. Maybe if you learn something about synchronization primitives, there was a classical story about dining philosophers. Maybe you learned something about that. And this David had in mind when he called this network the Dining Cryptographers Network. Some people would make a joke and say, hey, this is mainly the DC, the David Chaum network, and this is why he called it that way. But, okay, I don't know. But this is only names. How does it work? Let's assume I explain it using a small example. We have 3 stations, 1 to 3. Stations have exchanged keys. For example, station 1 and 2 have exchanged the yellow key. And one of the 2 is taking the key, and the other one is taking minus the key. And minus here, in my example, everything is done mod 16. Station 1 and 3 share the blue key. One of the 2 takes it positive, the other one takes it negative. Positive, negative means characters are added or subtracted. And station 2 and 3 share the red key. Again, one takes it positive, the other station takes it negative. Then the stations may send messages. This is what they really want to send. In this example, station 1 really has a message to send. Stations 2 and 3 have no message to send. So they are going to send 0, which is a neutral element within an additive group. And now each station does the following. It takes a message, the message it wants to send, be it the neutral message, and all the keys he knows, and adds them up. In this example, mod 16, but of course you could do it mod anything. I just avoided mod 2, because if I would do the example mod 2, we wouldn't see any difference between plus and minus. So does station 1, station 2 does the same, and station 3 as well. So if I did it in the right way, if you add up these 3 strings of hexadecimal characters, this is the outcome. If you add up these 3, this is the outcome. If you add up these 3, that is the outcome. And then globally, we are going to add the outputs of the stations. And if we do that, oh, surprise, surprise, the message which station 1 wanted to send originates here. Why is this the case? It's the case because first, the other 2 messages are 0, and each key value is added once and subtracted once. So this is really, really a nice trick to send something against an attacker who taps each and every line. The attacker taps this line, this line, this line. He's not going to learn anything who sends the message. Because if you're going to modify the key values, then we could, by changing the key value, just make station 2 send the message. Or even we could make station 1 and 2 send a message where the sum of the 2 messages is just this message. So depending on the key values you have, everything could be behind this value. So what does this procedure guarantee? It provides anonymity of the sender. And the statement I have to prove later on is that if stations are connected by keys, the value of which is completely unknown to the attacker, then tapping all lines does not give him any information about the sender. So what do we have? David Schaub, who was a cryptographer. When I started into that field, was more than kind of network engineer. David started as a cryptographer, not as an engineer. And they had the feeling, okay, what do we do? First, we exchange keys. Sure, this is what you do in cryptography. And then we make sure that these keys, which are exchanged pairwise, are added up once and subtracted once. That way the keys cancel. And what we will have in the global sum is the sum of all messages. And then he could prove in his seminal paper on the DC network that this provides sender anonymity in a very, very, very strong sense. Because first, it has a very strong attacker model. It assumes all lines are tapped. And it also accepts that some of the stations are controlled by the attacker. Of course, if the station is controlled by the attacker, this station doesn't contribute anything to sender anonymity because it's controlled by the attacker But all other stations, as long as they share keys, still enjoy full sender anonymity amongst themselves. So it's a very strong technique because it's working in the strongest attacker model possible. The attacker taps all lines and he may control many, many stations. And it still achieves what you would hope for, that the rest of the stations still enjoys sender anonymity. First thing, attacker model, very strong. Second property, information theoretical security. Let's assume here I did draw it in a way that we have pseudo-random bitstream generators, because of course we are using or needing a lot of transmission, because here in this example one station can send one message. So if another station wants to send one message, same procedure, of course different keys. So usually if you look for performance, keys probably will be generated pseudo-randomly. But if you can manage to exchange long enough keys, which are really random, then this is a procedure which provides information theoretic security. Now, of course, it depends how do you exchange keys. My usual example is, how much could I store on this one? It's 16 gigabyte. Probably for plain email, within a group of 1,000 people, it would be enough for many years. Of course, if we are sending large attachments, so plain email, it's just an email comprises what I'm willing to type in, then I would say 16 gigabytes, it's okay for 1,000 people, because it means 16 megabyte per person, and it takes an awful lot of typing to type in 16 megabyte. I wouldn't like to do that too many times during my life. But maybe you are faster in typing than I am. But okay. Of course, if it's about large attachments, then it's a completely different story. 16 megabytes, this is just a high resolution image of my video camera or of my photo camera. So surely it depends whether you can afford information theoretical security. It depends on how much service in terms of transmission the network is going to provide. But the good property is, if we have long enough keys exchanged, then it provides information theoretical security, which is a good thing. Because even if you are paranoid as a cryptographer, you will sleep well if you could provide for information theoretic security. Then overall you can say, hey, if it breaks, it's not my problem. If it breaks, it's the problem of the operating system guys, of the application designers, whatever. It's not my problem. So you see, this is the advantage for the cryptographers. So this was, I would say, a real breakthrough. It, by the way, gives us complete flexibility how we build the communication network. We just assume the attacker is going to tap everything. Therefore, we can just build the communication infrastructure for performance, not for privacy, because we are assuming the attacker taps it anyway. Okay, So let's see. How about our break? Yes, we should do some break. Or do you have questions first? Because this was a very fundamental idea of the DC network, so maybe you have some questions.
What if an attacker controls one station among these three stations that are sending message and modifies the message that he sends?
Okay.
And comprises the overall message chain.
If any of the stations misbehaves, then the outcome will be random. That is, then no message transmission. That is what we have to discuss in the long run, how to deal with modifying attackers. And we'll come across protocols which help to identify modifying attackers in the long run. So who doesn't follow the protocol properly can be excluded in the long run. But this will take some effort and have to discuss that. Further questions? Then maybe I should go back many slides and ask you a question which is a good question for an oral examination. What do this kind of message service and the DC network I just explained to you have in common? And I would say they have a lot in common. So maybe if a break is too boring, this is something you may think about. Now enjoy your break, 20 minutes. Do we want to restart? So far, I mentioned how messages are sent and what kind of sender anonymity we get. Of course, I should also mention how messages are received. And after we did add it up here, I assume that messages are broadcast back to all the senders. So senders get a feedback whether their sending succeeded, and everyone gets the same message by broadcast at the end of each round. And of course, with respect to broadcast, everything applies which we did discuss in broadcast. Broadcast has to be consistent, that is, each station gets the same message. And if you look at this picture, the keys here we have are used for making sending anonymous. Keys are not used in this picture enforcing the consistency of broadcast. Broadcast is as secure or as insecure as you implement it here. Later on, we'll learn an extension of the DC network. I will call it DC Plus network, where the keys we have here are even used to provide for consistency of broadcast. Putting it in another way, what you have here, the statement is, hey, the DC network is a network about sender anonymity. And this is provided in a really strong setting, in a really strong sense. But the DC network, as it has been originally published, doesn't say much about recipient anonymity. Okay. What of course we have to deal with is anonymous access. In the ring network, we had to spell out who is allowed to send when. And again here, we have to spell out which station is allowed to send a message when. Of course, there are extreme situations. Maybe you say, whenever I have something to send, I won't send. Okay, nice. As long as only in very rare situation someone has something to send. Otherwise, if many people want to send at the same moment, what you have is the sum of all messages, which usually is not really useful if messages are encrypted end-to-end. Because if it's encrypted end-to-end, usually you have to have the bits of each message separated to be able to decrypt it. Okay, so keep that in mind. We have to discuss anonymous access, and we have to discuss how to secure broadcast. And of course, in some sense, we have to prove this statement about sender anonymity. First, maybe for clarification, I should spell out that we have at least in the DC network 3 distinct topologies. Here I did make a drawing of the 3 stations we just had. And one topology we have is the topology of keys. We can decide, in building the network, we have to decide who shares keys with whom, which gives us the key topology. In the example we just had, there was some kind of trivial choice. We had everybody exchanges a key with everyone. So we had a fully connected key graph. This surely is an obvious choice if you have 3 stations, and maybe it's also a choice which is quite good if you have 4 or 5 stations. But assuming you have a few million stations, then exchanging a key with everyone, if you want to join the network, probably this isn't a good idea. So then key topology really gets an issue. Secondly, we have a kind of topology how messages are superposed. Going back to the slide we had here, over the break I got a question, hey, this global adding up, is this a 4th station? Is this an additional station? Or is this a kind of functionality each of the 3 stations does? And of course the answer is, it depends. One way to implement it is make sure that the local sums are just forwarded to some kind of central place and added up there, which means you have an additional station. Another way to implement it would be to make sure that each station sends its output to all other stations. And then everyone adds up its own output and the outputs of the other station. It got. So somehow we have to get our minds clear how superposition works, in which sequence we add up which parts of the global sum. And we have a third topology, transmission. Of course, we have to transmit messages in a way that the global superposition can take place. And it's pretty clear that the superposition topology and the transmission topology depend on each other. Usually, parts of the sum you want to add at a certain place have to be transmitted to that certain place, otherwise you can't add them up there. On the other hand, usually if you want to send two parts of the sum over a line, then it might be a splendid good idea to add them up before, because then it's only half as much you have to send over the line. So clearly, superposition and transmission have to do with each other. What does not depend on another topology is the key topology. How keys are exchanged works irrespective how you superpose, works irrespective how you transmit. So the key topology is independent of the two other topologies. And I would argue that this is really nice. Why? First, from an engineering point of view, whenever you have two properties which are independent of each other, for engineering, this is nice. Because for each of the two, you can develop your own policy how to make good use of it. So what makes engineering difficult is dependencies. Therefore, if two things are independent, usually it's a good idea. Makes engineering enjoyable. Now, if you look at our application, it's pretty clear superposition topology and transmission topology depend on each other. So if you construct a DC network, you have to think about how you want to superpose and how you have to transmit accordingly. So in building your network, you should fix how we add up globally. If you build your DC network, you haven't to think about the key topology. Keys may be exchanged arbitrarily. In the limiting case, nobody exchanges any key, but still it works. Not much of sender anonymity, clear, but it works. Or maybe in the limiting case, everyone enjoys exchanging a key with everyone else. Maybe even for millions of users. Okay, if they enjoy it, so be it. Let's enjoy them. Or maybe they have any other kind of strategy how to exchange keys. And I would argue that this is really a good property, not only from an engineering point of view, that you can do it and solve it separately. You can build your network, your basic infrastructure, and it's a completely different story how people organize themselves in exchanging keys. So it's different. That's nice. But in addition, and in particular for security and privacy, I would argue that it's extremely nice, because your decision how you build your basic network mainly has nothing to do with security and privacy. You just have to build it. For anonymity, it doesn't matter how you build it, as long as it's adding up globally. And the second story, how to exchange keys, This has to do with the security and privacy property the network is going to achieve. No keys, no sender anonymity. More keys, probably better sender anonymity. Exchanging keys with trustworthy stations is better, probably. For a normal user, exchanging keys only with stations controlled by the attacker, of course, this is useless. But the good story now is everyone within the system can decide for his or her own how to exchange keys. We don't need a global agreement who is the attacker and who is not. We can just leave it to the users and say, hey, if you have the feeling that Mr. Schäuble is the most trustworthy person within Germany to exchange keys with, then exchange a key with Mr. Schäuble. If you have the feeling, hey, this is not the case, I would like to exchange a key with, take some well-known hacker, I don't know their names, then you exchange a key with such a guy. If you have the feeling you trust in your bank, then exchange a key with your bank. If you have the feeling, Christian church is a good idea, then exchange a key with your church. It's up to you. It's not up to us as the engineers. So I would say that this kind of topologies, that the key topology is really independent of the other topologies, this is really a good thing. Because we as the engineers can build the basic system, and then the users can decide whom they trust. And in some sense, how paranoid they like to be. If you are completely paranoid, you are going to exchange keys with everyone. But probably you will then discover that paranoia in large systems really gets labor intensive. So somehow you have to keep your paranoia under control. Okay. By the way, it's a good exercise, and I don't know whether someone really thought it to an end, how you really should exchange your keys, assuming we have some kind of common feeling how trustworthy different actors are, or more in particular, what kind of actors we believe won't work together. So exchanging some keys with some, let's say, leading figures in Arabian countries and some leading persons in Israel might be a good idea, because usually you may assume they never ever will work together. So in some sense, as an engineer, I would say, hey, I don't care. You exchange keys as you like. And in some sense, this is the end of the story for the engineer. But of course, if you want to deploy a system, if you really want it to work, some people are going to ask you, the engineer, hey, how should I do it? You told me I can do it how I like it to, but please tell me, what should I like? And then again, we should have some good answers. And my starting point would be, hey, exchange some keys with persons or institutions where you have the feeling they won't work together against you. And because against you is difficult to spell out, because who are you? probably starting with some entities where you can state, I don't expect them to work together. It's a real starting point. Okay, this is only a very rough answer. Maybe if you are interested in social networks, in who is going to trust whom, in which respect, etc., there could be much more detailed answers. And I don't know them. For example, when the DC network was invented, it was in 1985. We didn't know much about social networks, at least no computer-based social networks. Of course, social networks and friendships, it's a very old concept. It's not invented by a computer scientist, not at all. But could we make good use of computer-based social networks for exchanging keys in the DC network, or figuring out with whom to share a key? I haven't an answer. I don't know literature about it. Probably there is no literature, because if there would be literature, I should know it. So if anybody is interested in that kind of work, okay, it's open. Research starts there. Nothing is known, except the very general rules. If you want to have security within a distributed system, don't put all your eggs into the same basket. So take advantage of the distribution. So at the abstract level, everything is clear, but in the concrete, it might be worthwhile to do some research. Okay, multi-access. One extreme case in multi-access is, hey, if you want something to send, send it. Works fine for small groups. For example, at the moment, we somehow work in a multi-access mode. If you want something to say, just say it. In this setting, works fine because, regrettably, it's a very rare event that someone of you wants to send something. If everybody wanted to ask questions nearly all the time, probably we would have to agree to a better procedure. One procedure to do it then better would be using a reservation scheme, that first we would have some round of interaction to figure out who is going the next person to ask the question. And then after we had figured that out, that person would be allowed to ask the question. Usually this makes a lot of sense if figuring out who is next, who may send, takes only a few bits, and if the messages themselves are long, they take many bits. So in the DC network, a reservation scheme could be done in the following sense. For each possible message to be sent, here in the example we take 5, each station, each Teilnehmer in German, sends 1 bit. So T1 wants to send message 2. T2 wants to send message 2. Okay. T3 doesn't want to send anything. T4 wants to send message 2 and 4. And T5 wants to send message 3. Now if we add it up, and not bit by bit, but mod something bigger, for example, mod 16 would work, you would see that if I'm adding up all zeros, okay, the sum is 0. Here, if I add it up, the sum is 3. Here, the sum is 1, sum is 1, sum is 0. So, assuming by broadcast everyone gets this reservation frame, then each station sees the following. The first frame we can just skip because nobody wants to send. Sending it is just a waste of bits. Frame 3 will be a collision because 3 stations want to send. So a good rule would be to say, hey, none of you is going to send, because it would be hard to figure out who of the 3 should send. So none is going to send. Let's skip frame 2 as well. Frame 3, great. 1 wants to send. 1 is allowed to send. Frame 4, 1 wants to send, allowed to send. Nice. And here again, nobody wants to send. Okay, let's skip that. And then we start anew with a new reservation frame. And probably the stations T4, T2, and T1 will try to get a frame reserved in the next route. Okay, this is how it's done. What is the price to be paid? The price to be paid is, after sending these bits, and before we finally can send the messages, we need at least 1 round-trip delay, because we have, of course, to have the outcome of the reservation before we can send the messages. That is, overall, in a reservation frame, or in a reservation scheme, you have at least 2 round-trip delays. If it would be a scheme where you could send directly, you could be lucky and have a 1 round-trip delay.
Maybe I'm not understanding it completely, but announcing I'm going to send a message next doesn't sound a lot like sender anonymity to me. How is it made sure that I have sent, I'm going to send a message, but no one afterwards gets to know I was the one sending that message?
Okay. These bits here are sent using the DC network. That is, nobody knows who's sending which of these bits. All what we get to know is the global outcome, the global sum. So we see nobody, 3, skip it, 1, good, 1, good, 0. That's all. Good question. Okay. More questions? Yes.
What do the bits represent? The bits of the message? Yes.
The bits in here, it's just a signal that I want sent. Nothing more, nothing less.
So the 1 bit means that I want to send some message.
Yes. Yes, yes. But in some sense, this is completely free. It's just a rule of encoding we can define. Of course, I could say, hey, if I would like to interchange 0 and 1, but I think the coding rules I just used are the most obvious ones, and they work fine. Okay, further questions? It is pretty clear, or I should mention it, if we would do the adding up of the reservation frame mod 2 instead of, for example, mod 16, then instead of 3, you would have a 1 here, which would mean that all the 3 stations which want to send had the feeling they have successfully reserved a frame for sending on later, which of course would mean that a collision would occur here. So this is the first argument, or first purpose, where I would say adding up mod 2 in the DC network often is not the best way to do it. Therefore, considering using a modulus which is larger than 2 is a good idea. When I started to explain it to you, I called it superposed sending. And this is what David Chaum invented. And later on, I did work for a simpler proof. And now I'm going to add something which I call superposed receiving. So now it's part of my PhD thesis. And the idea is, if some kind of collision occurs, no need to throw it away. Usually in radio networks, if you have a collision, you throw it away. Because a collision in a radio network usually means the result is undefined. In the DC network, if a collision occurs, the result is very well defined. The result is the sum. Mathematically, the sum. So, the good news is, everybody knows that it's the sum. Everybody gets the same result. Whereas in radio networks, if collisions occur, maybe at different places you have a different kind of collision. Here in the DC network, it's different. So, if a collision occurs, don't throw it away. Make good use of it. So the first observation is, whoever knows the sum of n characters and n minus 1 of these n characters, that person can calculate the nth character. That is, if you have the sum, if you store it, and somehow can manage to retransmit n minus 1 of the parts, then remembering the sum and having n minus 1 of the parts gives you the nth part. So don't throw the collision away. Very simple observation. It only took me 3 years to get at it. So simple after you've got it. But I can say many people looked for better solutions, so nobody got it faster than me. But okay, still 3 years is an awful amount of time for arriving at such a simple conclusion. So superposed receiving can be done in 2 ways, pairwise and global. Let's start with pairwise because it's simpler. So let's assume somehow we reserve or can reserve channels or slots. And then we may use superposed receiving, in particular pairwise superposed receiving, to enable 2 stations to send simultaneously. So each station, each of the 2 stations sends simultaneously at the same time. And then each subtracts their characters from the sum to receive the characters sent by the other station. So if you have a collision, you know what you did send, you can subtract it, and you get what the other party did send, assuming it's only 2 parties. So this gives you a duplex channel in the bandwidth of a simplex channel. So making a picture for it, so let's assume we have a station 1 and a station 2. Without superposed receiving, S would send here, for example, an X, which would be broadcast to S2, and S2 would send a Y, which would be broadcast to S1. So they need 2 slots to exchange X and Y. And in pairwise superposed receiving, it's simpler. You just reserve the same slot, S sends X, S1 sends X, S2 sends Y. So within the slot, by the additive nature of the DC network, you have X plus Y. This is distributed to the both S1 and S2, and S1 subtracts X, what S1 did send, receiving Y, and S2 subtracts Y and receives X, what the other station did send. So instead of 2 slots, you only use 1, which helps you save half of the transmission. Okay, gaining a factor of 2 always is an enjoyable procedure, I would argue. Next application, global superposed receiving. So this should work for any number of stations. So the idea is that the result of a collision is stored, so that if n messages collide, we make sure that only n minus 1 of them are retransmitted. For the procedure to work, we will use a collision resolution algorithm, which will calculate the mean of the messages which collided. So the DC network will add up the messages, so you know the sum of the messages. So if in some sense you can count how many messages did collide, then you could divide the sum by the number of messages, so you have the mean message. So this is the basic idea. To do so, we need a message format where here in the middle part we have the message, and then we have some leading zeros just to make sure that if messages are added up, we don't lose carries here. In the end, we just have a 1 to count how many messages collide. So this is a kind of counter. And again, we have to have enough zeros to make sure that we haven't a carry, or don't lose a carry. So this is the message format. And now probably the procedure is explained most easily by means of an example. If you would program it, it would be a recursive procedure and it looks complicated. But if I explain it to you using an example, it's really easy. And I would say it's enjoyable. So here you see 5 stations sending 5 messages. At the right-hand side, you have the ones, which are counting the number of messages. And at the left-hand side, you have the particular values of the messages. Okay? So we add up the number of messages. It's 5. 5 messages collided. And we add up the values of the messages. So 7 plus 15, it's 22. Plus 4, it's 26. Plus 1, it's 27. Plus 5, it's 32. And now we are going to divide 32 by 5. So it's 6 point something. And let's assume we are taking the largest integer, which is small or equal to the value we just got. And now let's state the rule that in the next step, only those stations are entitled to send which want to send a message which is smaller or equal than 6. So the criterion here is smaller or equal. So let's go through the stations. S1 wants to send 7. 7 is not smaller or equal than 6, so S1 will fall silent in the next step. Same for S2. S3, S4, and S5 have messages which are small enough, so they will resend immediately. So they do. So 3 stations send again. So in the right-hand field, we have a 3. You know we have a collision of 3 messages. And 4 plus 1 plus 5 yields 10. So this is the sum of the 3 messages. So again, we are dividing 10 by 3 and taking the largest integer, which is small or equal, then what did it just get as the result of the division? So in this case, it's 3. And now we apply the procedure recursively. We say, okay, within the stations which just did send, those are entitled to send in the next step, which have a message which is smaller or equal than 3. And this, in this case, is only station S4, so S4 is sending again, and all others fall silent for the next step. So the outcome is, of this step 3, we have one message, and it has the value 1. Hooray, we have first got our message, the first message we did receive. Now I said stations fall silent. Here, in step 3, it's successful. All is finished. Now, those other stations which after this step decided to fall silent may send. But in practice, there's no need that they send, because what they would send can be calculated easily. Because if you know, hey, here we have 3 messages and they have the sum 10. Here we have 1 message and it has the sum 1. Then if you let the others send, which were silent for 1 step, it's pretty clear. It's 10 minus 1, it's 9, and 3 minus 1, it's 2. So in the next step, if you would let the station send, you get 2 messages with the sum of 9. That's it. So, but because we already know what will be the outcome, of course we can save time and energy by just doing the calculation instead of doing the exercise with all the transmission. And now again, same procedure as last year. We divide 9 by 2, 4.5. We take the largest integer, which is small or equal, it's 4. And now it's pretty clear out of these two, if someone has a message of 4 or smaller, send it. Okay, S3 does so. And okay, hooray, second message received. Now, of course, the other station is in its role to send, but again, we can calculate what the outcome would be. 9 minus 4, 2 minus 1, yields 5 and 1. No need to send it, can just be calculated. Here we receive the third message. And you see all this branch of the tree we did work on, finished. Now we have to go back here and say, and now everybody who did send here and has a message larger than 6, please send. But again, this can be calculated. 32 minus 10 is 22. 5 minus 3 is 2. Calculated. Here again, 22 divided by 2, 11. And the next step, S1 is going to send. S2 is not going to send because 15 is larger than 11. So, fourth message received. Again, we can calculate the next message. It's 15. Fifth message received. Procedure completed. Okay, so this was a procedure. Now looking at how it works and what did it achieve. How many transmission steps did we need? 1, 2, 3, 4, 5. We had some collisions. We did do it recursively. We did never throw anything away which we got. And we managed with the minimum amount of transmissions. If you want to send 5 messages, you can't do better than having 5 transmissions. And this protocol obviously manages to work with 5 transmissions. So, in some sense, optimal. What's the idea behind it? How could you argue that the protocol has this property? Here I said we are calculating the mean message, and assuming for the moment that no 2 messages are equal, then if you calculate the mean message, then there always must be 1 message above and 1 message below the mean. So in our decisions, where we apply this criterion, it's pretty clear that both sets we are dealing separately with are non-empty. That is, we make sure in each step we are splitting the set of senders in non-empty subsets, which we can then deal with separately. And this gives a nice property that finally, if you split and split and split and split, sooner or later you will end up with a single sender sending a single message. And then you can go back recursively and so on and so forth. It's pretty clear that whenever we send, we have a 1 round trip delay. So it's pretty clear if I say we have a need of 5 transmissions, and who is going to transmit depends on the outcome of the round before, then it needs 5 round trip delays. But again, I don't see a way how to do it better. And I would assume if you are not talking about a reservation scheme, which has at least 2 round trip delays, but of course, if it works out well, then after 1 reservation allows many messages to send. So if you do without reservation, I would say that you can't do better than with the 5 round trip delays in this example. Now let's assume, or let's look at what happens if 2 messages are equal. Because in my example before and in my argument, I assumed that messages are not equal. So what happens if two messages are equal? So you see that S3 and S4 here both want to send a message 4-1. So what will happen? Here we have two messages with the sum of 8. Eight divided by 2 is 4. So both will send again. And this now is some kind of result we can test for. If in the next round you have the same outcome as in the round before, then all the messages are equal. Because otherwise, you would split them in two sets which are both non-empty. And if all are equal, and you take this criterion, small or equal, then one set comprises all and the other set is empty. So after you got here the same result as there, you know both messages are equal. You know their sum. You know the number of the messages, so you can divide and receive the messages. So even if messages are equal, it doesn't change anything. After 5 steps, the game is over. Now, if you go in the extreme and say, let's assume 3 messages are equal, then the procedure even gets faster. But of course, to admit, it's extremely unlikely that 3 messages are equal, if you're talking about longer messages, sure. So what do we have? I'm going back. This procedure of global superposed receiving, I would argue, is really a splendid good access protocol, because it has all nice properties an access protocol should have. What are nice properties of access protocols? The first property would be an access protocol should be fair. All stations who want to send should get service before other, which later on want to send, get their demand fulfilled. So here, it's fair in the sense that all stations who have a collision first can send their message, and only after additional station can send messages. Okay? Fairness was the first thing. Second thing, maybe I call it dynamics. In a good multi-access protocol, if only one station wants to send, it should get the full bandwidth. So if only one station wants to send one message after the other, it gets the whole bandwidth. And when another station jumps in, then fairness again makes sure that the bandwidth is shared between the 2, or the 3, or whatever number of stations you have. Third property. If the channel is empty, it should be possible to send a message with one round-trip delay. Shorter is impossible. You can't send a message faster than with one round-trip delay, but it shouldn't take longer. Why shouldn't it? If the system is not loaded, it should be possible with one round-trip delay, which rules out all kinds of reservation schemes, of course. So one round-trip delay works. So these are the basic properties of multi-access protocols, and I would argue that this protocol fulfills them all to the best degree possible. Maybe some additional properties, some people would like to see priorities in multi-access protocols. How about priorities? Do you have any clue how to add priorities in this scheme? Look at the outcome. In which sequence do we receive the messages? We receive 1, 4, 5, 7, 15. Hey, receiving starts with the smallest message. Why? Because we took the criterion small or equal. So this scheme, as described here, gives priority to smaller messages. By the way, if you would like to have priority for larger messages, then just change this criterion of smaller or equal to larger or equal. Then you will receive the largest message first. So it's pretty clear how you add priorities. You take just 1 bit, interpreting them as high-end bits, and those of your message, and those are the priorities. So I did this protocol, I invented this protocol in my PhD thesis just to make good use of the DC network. But my feeling is this kind of protocol has not only value in anonymous multi-access, but it could have value whenever you have a channel which has additive structure, irrespective of any kind of anonymity, because it's so efficient. Okay, so this was multi-access. If you are a hardcore programmer, of course, you don't understand now anything. First, you have to program it recursively, and then it's pretty clear. Okay. But still, I feel it's easier to explain using an example. Any questions? Okay, if not, then how would we build it? Going back to the topologies, I said superposition topology has to be chosen. Transmission topology has to be adapted accordingly. And how to do it? How to do it if we want to have a very small delay in the channel. And this now is the theme, how we could do it in principle. Let's assume we have m inputs. What is the fastest way to add up, in my small example mod 2, m bits or n sequences of bits? The fastest way to do is just take an adder, in this case an XOR, and connect them as a binary tree. And then you make sure that after log 2 steps, you have the overall sum. And of course, if you want to broadcast this, and if you have a better amplifier than just the logical gates, then you just take logical gates as amplifiers. So the main statement taken from this picture is, if you want to add up m streams, it's causing a delay of log 2 m, not a delay of m. you can work with the logarithm. And at least for larger m's, this really is a good idea. Next question. I argued that having a modulus for adding up which is large, at least which is essentially larger than 2, is a good idea. Why? Let's go back. If we would have a modulus of 2 here, we would misinterpret the outcome of the reservation scheme. If we want to do a procedure like this, we have to have a very large modulus, such that we really get the sum of the messages. Okay? In this scheme, the modulus has to be so large that it covers this whole length. So the question is, how to implement a DC network with small delay but large modulus. And probably, if you start thinking about it, your first idea is, hey, this is impossible. I cannot get shorter delay than the modulus I'm using. I have first to add up with respect to the modulus before I can send anything back via broadcast to the stations. And luckily this is wrong. Let's see. So this is not, let's say, an implementation description. It's mainly a description to give you an idea how it might be done. So let's assume we want to add up information units and keys, which are all coded binary. But we don't want to add them up bit by bit, mod 2, but mod some larger modulus. For example, we want to add them up to some 2 to the power of something. And this something may be 1,000 or 10,000, I don't care. Then we can do the following. Bit by bit, we can add up, it takes the carry, count how many positions we have, still we have to ignore the carry, and then start from scratch. So the good idea is, if you take your modulus as a power of your base where you do the encoding of the single units of your storage and transmission, here bits, then you can still transmit something before you have your end result. Same how do you do calculations in the decimal system if you add up numbers. After you did add up the rightmost digits, you could just send them because it's already determined, and then you work to the left. So the argument that you first have to have the overall result before you can send anything obviously is wrong if you do it in a clever way. And this picture mainly is a proof of concept that this can be done. So for local superposition, you will add up the keys and the message, and you can start sending bits to the global superposition well before you have the last unit processed. And again, in the global superposition, you can do the same trick. You get streams, you add them up, and you can send bits well before you did process the last bit. So the main statement you should take with you is that having a large modulus doesn't enforce that you have a large delay. And this is very important for the multi-access protocol we talked about, because some of the multi-access protocol made good use of having a large modulus. And I argued that the multi-access protocols really are nice. In some sense, I'm very proud about them. But of course, this makes only sense if requiring a large modulus doesn't enforce a long delay. Because a nice multi-access protocol, if it enforces a long delay in the channel, is not really a good idea. Okay, so this was this slide. Let's see how, okay, still 13 minutes to go. Okay, any questions so far? Then let's work a little bit towards the proof of sender anonymity. First, what you hopefully remember is the Vernam cipher, the one-time pad. Do you remember? If we had a 0 here, which we wanted to transmit, it could be a 1 and a 1, or it could be a 0 and a 0. And if you had the coding key values here, it decrypted accordingly. If we had a 1, it could be a 1 and a 0, or it could be a 0 and a 1. And if we had the corresponding key values here, it decrypted accordingly. And this provided information theoretic security. And now in some sense, the DC network, the superposed sending network, comes pretty close to that. You see, there may be a message bit we want to send. There's a key. And assuming we have only 2 stations to make our example closer to the one-time pad, then we have the same key value here. Making sure that here the 2 key values cancel. As the 2 key values cancel here, by this addition, in the DC network, the 2 key values cancel here. And as we had the ciphertext here we have the outcome of the local superposition. And now what's the difference? Why can't we argue that if the one-time pad provides information theoretic security for encryption, why isn't it trivial that the DC network provides information theoretic sender anonymity? The problem is that in the DC network, in the one-time pad encryption, the attacker only sees this, right? The ciphertext. if he could make sure that in the DC network, the attacker would only see the outcome of one station, we would be finished with the proof. Then, if the attacker would only see this, it would be absolutely the same as in the one-time pad case. But the attacker is also going to see the outcome of this station, so the outcome from here. And what is in this station is not completely independent of what is in that station, because these two stations share a key. They share a key value. Therefore, if you look at it from some distance, it's pretty close. What was here, the ciphertext, now here is the result of the local superposition. But within the DC network, it's not only that the attacker is assumed to get the output of one station, it gets the output of all stations. And this makes it necessary to come up with a proof for the DC network. So I said everything orally. Here we have the key, the message. Here we have the message, the key. The key is shared with the other one. This is minus the key. Okay. So the analogy between the one-time pad here and the DC network there is that if you take the ciphertext here and the output of one station, then obviously it's the same. You have a key and a message. You have a message and a key. What is sent and taken by the attacker is the sum of message and key. And the difference between the two is that in the DC network, this key from this station is also part of another station's key set. So we have not only to consider one output, but the output of the other station as well. So within the DC network, we have more dependencies. We have to consider in our proof of security. So on the one hand, there's something to be done, and we'll do that either today or in a week. But on the other hand, the basic idea of the one-time pad can be taken over to the DC network with respect to sender anonymity. What was the basic idea? The basic idea was the one-time pad protects the message. Behind what is sent here can be any message value. And the same here. The output of the local station protects the message value. Behind this local sum can be any message value. So this is a basic understanding of sender anonymity within the DC network. And now, let's see whether we have the time to really go into it. No, I think we don't start, because now it takes me 10 minutes to finish the proof, and this wouldn't be fair. So we'll continue here in a week. So see you in a week.